Hello, my name is Anubhav and I am ESR 15 in the InnoDC consortium. This presentation is part of a series of presentations that make up deliverable 2.5, describing the tools developed in Work Package 2 for analyzing resonances, design, and control interactions. My project investigates the black start and aligning capabilities of offshore wind power plants. This has majorly two motivations, one from the TSO perspective and the other from the wind power plant operator's perspective. Currently, wind turbines are not anymore just passive units that connect to the grid, but are also required to support the grid during contingencies, especially because more and more renewable integration is pushing the dynamic stability limits of the existing grid system. Wind power plants provide ancillary services like real power control, reactive power control, power factor control with ramp rate constraints, but more advanced and services like reactive current injection are being demanded by new grid codes for low voltage ride-through and reactive power stability. Presently, wind turbines are exempt from frequency stability and restoration services, but inertia emulation for fast frequency response and power oscillation damping, along with local voltage control for controlled alienated operation, are expected in the upcoming grid codes. As far as power system restoration is concerned, although NSOE does already include the black start and islanding capabilities as options for wind power plants where TSOs can request these functions, the active participation of wind power plants early on in the system restoration right now is very limited. This is because traditionally wind turbines are controlled as grid following units, which means they require an external grid voltage point to connect to. Right after a blackout, the network might not be stable enough, and thus early connection of wind power plant can lead to a recurrence of a blackout. As far as the wind power plant operator is concerned, right now wind turbines rely on auxiliary sources, mainly a diesel generator on the offshore substation for energizing the offshore network cables, transformers, and even creating the offshore collector grid when the main grid is out. This diesel generator involves costs due to or is associated with large costs due to space it occupies offshore, maintenance requirements for shipping related downtimes of about 3 to 6 months, insurance costs due to an extra fuel tank, backup diesel generators, and safety constraints. Grid forming wind turbines or black startable wind turbines can allow wind turbines to participate earlier in the power system restoration because now wind turbine doesn't need to wait for the network reconstruction to finish, but can instead act as a black start unit to provide green, high power, fast black start, and also defend against potential cascaded blackouts by doing trip to house load or controlled islanded operation. This ultimately reduces the restoration time, the unserved load, and thus the overall blackout impact, leading to cost savings. For the wind power plant operator, a self-energizing wind turbine or grid-forming wind turbine can help minimize the dependence on the diesel generator offshore because it can energize the offshore collector cables, the transformers, and even operate without without requiring an external network. This can reduce the downtime due to shipping during refueling, save costs because of the free up of the offshore space if a diesel generator is not required anymore, increase even reliability, and ultimately also not to also it's important that the carbon emissions associated with the operating of the diesel generator are displaced. Before I jump into the PSCAD files to show the models that have been developed, the different controls that have been implemented, and the simulation studies that have been performed, I would like to give a brief overview of the system through this schematic. So what we have here is a two-terminal point-to-point connected HVDC link, with the left-hand side being the offshore terminal and the right-hand side being the onshore terminal. The offshore wind power plant operates in grid forming mode, which means it controls the voltage and frequency of the offshore collector grid. Thus, the offshore MMC controls the voltage of the HVDC export link. The onshore MMC then controls the voltage and frequency of the onshore PCC because there is no grid available. Instead, we have a block load which is energized to demonstrate the black start capability of the HVDC connected offshore wind power plant. The wind power plant consists of 50 turbines with a partial aggregated model. So this means that the first string has 9 individual wind turbines, the second string is an aggregate of the 9 wind turbines, and then the remaining 32 wind turbines are aggregated into one model. Each wind turbine model has this structure. So you have the voltage source, because this is a grid forming control, and thus the wind turbine behaves as a voltage source connected to the filter, inductor or filter of the converter, and then the wind turbine transformer. We have implemented 4 different grid forming controls to control this voltage source, but of course this can be enhanced and changed. So now I would like to give a tour of the PSCAD files and show you the different models, controls, and simulation studies. So this is the PSCAD model of the system that has been developed. I gave you a brief overview in the schematic before, but now I will show the different components and the controls that have been implemented. So this is the main page. As you see, it's a point-to-point two-terminal HVDC link. This is the onshore terminal on the left. Here is the HVDC cable. Then on the right, you see the offshore terminal, which is connected to the wind power plant. We have these 2 pages here, which is the one is the operator console. So you have all the different settings, the times, the gain values of all the different components from the onshore terminal, offshore terminal, wind power plant control, and etc. And this page we have the plots. So the main plots of the powers, the currents, converter valve voltages, HVDC link, and other such important signals. For the onshore terminal, we have the AC network as a strong grid model, Thevenin grid equivalent, which we do not use for the purpose of this study because it's a black start study that we perform. So energization of the wind power plant and the HVDC link and the onshore side operates in an islanded mode. So instead we have a block load about 30 megawatt, and the onshore MMC operates in islanded operation, which is opposite to what it would do in a normal operation. So the normal mode, you would have the onshore grid connected, and the onshore MMC would operate in VDC Q control. So it would control the DC link voltage of the HVDC link and the reactive power injection into the onshore terminal. And the offshore terminal would be responsible of controlling the offshore voltage and frequency. So it would be working in islanded operation, to which then the grid following wind turbines would connect. But however, we do energization from, or a black start from, the wind power plant side. So the wind power plant is in grid forming mode, controls the offshore voltage and frequency. Thus the offshore terminal MMC controls the DC link voltage of the HVDC link, and the onshore MMC thus operates in an islanded mode, which means it controls the onshore voltage and frequency, to which then a block load is connected for energization, demonstrating the energization capabilities. Now both MMC terminals are the same. So you have the MMC control in this block here with the transformer, the converter transformer, and the converter reactor with the PIR if needed. Each MMC is modeled with a detailed equivalent model. So each arm consists of 225 submodules, but they are during the modeling they are grouped together to solve the circuit, and then again again the model, the group model is split so that we can see what's happening inside the submodules. And there is control of the circulating current, so circulating current suppression control that is present, which is to reduce, to eliminate currents that flow between the submodules due to an imbalance in the capacitor cell voltages. And inside the submodules, you have the PWM generation and sorting algorithms, the inner controls of the MMC. The MMC control modes. So in this terminal, you can set up the different parameters of the resistances, capacitor values, inductors, filters, etc. And you have the choice to set which control mode you want for the MMC. So if you set it to islanded, it would as right now it's set, the onshore is set to islanded control mode, and thus it's shown here in this by this color, while on the other hand the offshore is set in this VDCQ control, and it shows here in this color. The two models are the same, so the offshore MMC and the onshore MMC are the same. However, there's a difference in this onshore MMC model because for the pre-charging during the energization, which I will show in a bit when I show the energization sequence, but what we do is that from the offshore side, the wind power plant energizes the offshore transformer and the MMC cells. So the offshore MMC charges from the AC side, recharges from the AC side, and then starts to control the DC link voltage. And then the onshore MMC is pre-charged from the DC side. So the DC voltage pre-charging happens, and due to this difference, there is some extra controlled pre-charging required to avoid significant transients over the HVDC link and energy due to the energy oscillation between the offshore cells and the onshore cells. So of course there are more enhanced closed loop controls, but we implement a very simple pre-charging sequence which is implemented in this block here, and it's a very simple straightforward sequence in which we just pre-charge the upper arm first, and then with the lower arm bypassed, and then pre-charge the lower arm and with the upper arm bypassed without any control over the closed loop control over the valve currents, but that can also be implemented if required. In the middle, you have the HVDC line. So right now we have modeled a 200 kilometer export cable, and there is also overhead transmission line model if such studies need to be done, but for the purpose of our studies we use the cable model. Coming to the wind power plant, so as said before, sorry that you see some results now. I have already simulated it because it takes some time for the entire simulation to complete, but I will go into the results a bit after the model. So we have this 50 wind turbines modeled in a partial, so it's a partial aggregated wind power plant. So each 9 wind turbines on one string, then 9 others aggregated into one, and then the remaining 32 aggregated into one. And the cables, the array cables that you see here are for now coupled pi models because they are relatively short length cables compared to the export cable. But of course, for more detailed studies, these can be also made into frequency-based phase models for modeling more transients if they are longer. And here are all the controls for the breakers for the sequence of energization. So right now what we do is we can simulate either all wind turbines energizing simultaneously all together, or which is more unrealistic, but for the detailed studies that we are going to perform later in the next phase of the project, the sequential energization is what is also more realistic and would be looked into to study the synchronization transients and sympathetic inrush phenomena, etc. And what you see here on the left corner is there's an option for doing soft start energization or hard energization. In the soft start, basically what it means is that as the wind turbines ramp up the voltage slowly, everything is connected. So the pre-insertion resistor of the offshore to energize the offshore transformer and the converter cells is bypassed, and everything energizes all together with the wind turbines. However, if you choose the hard switching, then of course, first the wind turbines are energized in one go, and then they connect to the offshore network with the PIR inserted, and then after some time a PIR is bypassed. I'll show you a bit more detail the energization sequence in later, which would help make things more clearer. Now, the wind power plant in each wind turbine model is the same. It's an average model of the wind turbine grid side converter. So we just have a voltage source connected to the filter inductor capacitor, and then the wind turbine transformer. And the wind turbine transformer is right now modeled just as a pure impedance. So there is no magnetic inrush and saturation, which is the focus of the next phase of this work. The references for the voltage source is generated by the control. We can have grid following controls or grid forming controls. Right now, the model just because the purpose of this work is to look into energization capabilities and islanded operation of the wind turbine. So we studied grid forming controls. And right now we have implemented 4 different controls, namely the direct power control, the virtual synchronous machine control, power synchronization control, and the distributed PLL. However, these can be enhanced, added more controls like synchro converter and other VSM based controls can of course be added. All the controls are implemented in this one model. So after entering the values of the resistances, the filters, uh, you can enter in the input what grid forming control you would like to use, and this is what is indicated by this this shows what grid forming control is being used right now by the wind turbine. And many studies can be performed with a mix of different wind turbine controls, if that makes any sense, or choosing some wind turbines as grid forming or some as grid following. However, right now we choose the entire wind farm as grid forming as a whole. And here you can see the most important signals: the wind farm voltages, the frequency, powers. So this is the power of the entire wind farm collectively, and these are the shared. So the what each wind turbine produces in terms of the power, voltages, and currents. And as you can see, there is good sharing, just as an example in this study that has been performed with the direct power control. I think this would be good enough details to show. We could show maybe the MMC control just from the top, from an overview point of view. So this is the entire MMC control. Here you can see the current control loop that is used to generate the references for the voltage, the PWM reference, and we have the third harmonic injection also there to utilize the DC link voltage to the max. And on here you see the outer loops. So you have the power control, DC voltage control, and the Q axis, the reactive power control. There's also the islanded mode control, so to control the voltage and frequency. Additionally, this frequency control has been implemented, which basically means that if there is a deviation on the onshore frequency due to, say, load changes, that would be communicated to the offshore frequency via this change in the HVDC link DC voltage. And this is to basically use the wind power plant also for supporting any frequency deviations on the onshore side without any communication links, but using the HVDC link as the communication variable. Yep, I think that would be it from a good overview of the entire system. Next, what I'm going to show is the different studies we have performed. So, as an example of what studies we have done and some results, just to show how we use the data from this model for analysis. So just to show the different steps of the energization sequence to give a more clearer understanding. First, we start with the offshore networks, which can be energized in, as I talked before, through hard switching or using soft startup. So in the hard switching case, we energize the grid forming wind turbines. Then we connect the offshore transformer and the MMC cells through this PIR, which is then bypassed after a pre-insertion time once the transients have died down. For the soft start case, this entire network is connected from the beginning and without the PIR, and the voltage of the grid forming wind turbines is ramped up slowly to energize to keep the transients controlled. Once the offshore network is energized, then the offshore MMC can be deblocked to control the DC link voltage of the HVDC link, which is then used to precharge the onshore MMC, as I showed with this controlled precharging sequence. After that, once the cells are fully charged to their rated values, we can deblock so that it starts controlling the onshore voltage and frequency. Finally, the block load is connected to demonstrate the energization capabilities of this HVDC connected offshore wind power plant. Some of the studies that we have performed are first to look at different grid forming controls and how the offshore wind power plant voltage and responds to the different transients of the different stages. So the offshore energization, the DC link energization, and then the onshore PCC energization, and how the voltage and frequency transients and the power and reactive power, the real and reactive power transients look for these different stages. And the results have been summarized in this article, which is under review for wind energy science. Another study that we have performed is to look more on the HVDC transients. So for the offshore network, do a sensitivity analysis for hard switching and soft start cases by changing the PIR and the PIT values, and also for the soft start for the different ramp rate values. And for the onshore MMC, the controlled precharging was implemented to reduce the dip of the HVDC link voltage and to control the transients due to the oscillation of energy between the offshore and onshore MMC cells. And the results of this can be found in the promotion work package deliverable 3.7, and more details have been published, which are under review for the Renewable Power Generation Journal. Next, I would like to show some Python scripts that we have developed just to use the data from the PSCAD models for the analysis purposes. So I'll just try to give a brief overview of how we use Python-based scripts to do some enhanced analysis of the data that PSCAD outputs. So in the simulation file, we have this plots page where you can see all the signals of interest, and you can also go into each component, or for example, the wind power plant, to see some specific signals. However, PSCAD provides something called as automation library that allows to use Python-based tools for enhanced post-processing and other enhanced features that maybe PSCAD doesn't have intrinsically. So for example, what you can do is you can use this automation library to open a specific simulation file in the workspace, change different settings, set the values of different parameters, and then ask the PSCAD simulation to compile and generate an executable file. What you then get is an executable file, and for which you can just write a simple batch file, a Windows batch file, to run this executable with certain parameters. And while this runs in the background, of course, you are free to do other tasks and even take benefit of automation and parallel processing. And then what we also did is to use this data that PSCAD generates for storing it for future usage. So for example, for the DPC mode, what we have here is a folder that contains all the output files that PSCAD generates for the different signals of interest that you want to store. And you have this info file that you can read to basically understand what the structure of these signals are, so the units or the part of the groups, and how they are stored as the time series in a time series format. And once you have this data, this can be used for very enhanced analysis or fancy plots. For example, we do some sensitivity analysis for the hard switching by changing different values of the PIR and the PITs, as I talked before, and we just wrote a simple function to calculate the energy dissipated by the PIR from these data files. And what you can get is then some fancy graphs, for example, for the voltage and the power waveforms of the different values of PIR and PIT, all overlaying on one another with, of course, using Python's advanced formatting tools. And then also you could make some fancy histograms for some better analysis, as shown here in the energy dissipated for different PIR and PIT values. And this allows to essentially avoid using tools like MATLAB or Excel, which act as intermediaries between PSCAD and for your data processing. And you can just also, since this is all open source, this provides a very good benefit for future reuse, and also avoid proprietary costs. So having studied the high-level target states in the energization sequence, namely the controlled islanded operation of the HVDC connected offshore wind power plant and how it deals with the different transients while doing grid forming of the offshore network, the next steps are, of course, to look inside the wind power plant and ensure stable parallel operation of the wind turbines in the face of these demanding transients, and how they impact the DC link dynamics and rotor side converter control inside the wind turbine. Thus, the next studies are related mainly to the sequential startup of the wind turbines inside the wind power plant. This will help refine control strategies for dealing with synchronization transients and phenomena such as sympathetic inrush related to the wind turbine transformer energization. This, however, requires an increase in the level of detail of the wind turbine model to be used. So this is what the structure of the wind turbine model with an increased details would look like. So on the left, you have the grid side converter, which is represented by a switching model with appropriate grid forming and grid following controls and the PWM details. And on the right of the DC link, you have this is the DC chopper, but and then on the right you have, instead of using the machine model and the detailed machine models and converter model for the rotor side, what we use is a current source which is fed by this IDC reference, and this IDC reference is generated by this extended IEC model, which consists of the standard mechanical model for the rotor and the aerodynamic equations using the power curves, and also having a representation of the pitch control dynamics. Why this is enough to study these transients is because the rotor dynamics are much slower than the electrical or the DC side dynamics. This this detailed model would help study how the energization transients would impact the DC link and the rotor side converter control, and also shed light on the capability of the wind turbines to deal with the transients in a controlled manner independently, and also give insight into any storage that is to be uh, integrated to deal with any limitations. For ensuring stability and robustness of operation, some interesting studies would include disconnection of the furthest wind turbine and then reconnection to which would represent a hard switching event. And then for the soft start energization, it is important to do fault studies to ensure stability and robustness during the entire energization process. Because, for example, resonance can be triggered during the post fault voltage recovery. Some long-term studies include capability assessment. This means system level studies to see how the wind variability affects the black start service or the voltage stability at the onshore PCC. And also an interesting study to do is the CO2 displacement, to analyze the CO2 displacement by these grid forming wind turbines, as they would replace or minimize, at least minimize, the use of the diesel generator on the offshore substation, and this would ultimately translate into cost benefits. So this concludes the part of deliverable 2.5 that presents the tools developed for studying the black start and unlanding capabilities of HVDC connected offshore wind power plants. Please feel free to contact me for further information on the models developed, controls that have been implemented, and studies that were performed. Thank you for your attention and your interest.